Namaskar, welcome to the channel Anka Ananda Haran. In the previous video, we have done some of the problems of article 1.2, 1.5 and 1.6 of Gilberstein book, but still few more problems are yet to be done, which are significant and unique in some sense. So here question number 5 we could not do in the previous video, but question number 4 and question number 6 are already being done. So here let us discuss question number 5. Here A is a matrix 2, 3, 3, 0, 5, 7 and 6, 9, 8. And we are expected to convert it into LU factorization. Then we have to find out C such that UX is equal to C. And we are expected to write UX as well as C. So now let us do that. So here this 6 is to be made 0, hence to make this 6 0, we are expected to do this operation R3 minus 3 R1 stored in R3 to get the upper triangular matrix U. So here minus 3 will be replaced by plus 3 in L. So the L is nothing but E31 inverse, which is our 1 0 0 0 1 0 3 0 1. So this is my L. And we have the matrix A system of equation Ax is equal to B, A is equal to Lux is equal to B, let Ux is equal to C, that means Lc is equal to B. Now that implies L, this is my L matrix, this is my C vector, so Lc is equal to, this is my B vector. So from the equation C1, 1C1 is equal to 2, 1C2 is equal to 2, 3C1 plus C3 is equal to 5. That implies C1 is equal to 2, C2 is equal to 2 and C3 is equal to 5 minus 6, that is minus 1. So I got my C1, C2, C3. So Ux is equal to 2, 2 minus 1. That is, if I want to write down in the system of equation format, that is, this is my U, this is my X and this is my C. So it is the Ux is equal to C format, which was expected to be done from the question. Now here find the product FGH and HGF. So here FGH are three elementary matrices of 4 cross 4 matrix. So here H represents this operation, that is R4 plus 2 R3 stored in R4. G represents R3 plus 2 R2 stored in R3. F represents the elementary row operation R2 plus 2 R1 stored in R2. Now that means if I have, this is my H matrix, here when I am multiplying G from the left, that means this corresponding row operation will take place. So here which row will change? R3 row will change. And that too, what will be the change? That is 3 2 position. In 3 2 position, I will, that is second row of H. Second row of H will be multiplied with 2 and it is added to row 3. This. So that means this is the change. So rest all elements will remain same. So rest all rows are also same. So this is my second row. Now when this matrix will be multiplied by F from left hand side, this row operation will take place on this matrix. So that means second row will change, rest all rows will remain same. And second row will, this position element will replaced by how much? R2. So this row, first row is multiplied with 2 and added to second row. So that means 2 will be written here. So my FGH is equal to this matrix 1 0 0 0 2 1 0 0 0 2 1 0 0 and 0 0 2 1. Next question is HGF. So this is my F matrix. Previously this is given, it is my F matrix. F on the F matrix, I want to do this G operation, that is I want to multiply second row with 2 and add the resultant to third row. So I will get 4, 2, 1, 0, 0, 0, and rest all rows remain same. Then I will multiply H to GF. What will happen? That is, third row of GF will be multiplied with 2 and the resultant will be added to fourth row. So that means the other three rows remain as it is, and here it will be 8, here 4, here 2, here 1. This is my final matrix. So they are very simple if we are directly applying the properties of elementary matrix. Otherwise, it will take a lot of time to do. Now, question number 9. Under what conditions is the following product is singular? So here this is a observe here, L is having diagonal elements 1, 1, 1 and U is having diagonal elements 1, 1, 1. That means this D of the diagonal D or diagonal matrix D represents all the pivots of A. So if all the pivots of A are non-zero, then it is A is non-singular. That means if D1, D2, D3 all are non-singular, A non-zero, then A will be non-singular. This is the first question's answer. Second question, solve for the system AX is equal to B starting with LC is equal to B. So here L is given in the same operation we will do. So say with the same matrix we are doing. L is given, it is multiplied with C, that will give us 0, 0, 1, that is B vector. So from which directly we are getting C1 is equal to 0, minus C1 plus C2 is equal to 0, that is C2 is equal to also 0, and C2 minus C2 plus C3 is equal to 1. This is the equation, which implies C3 is equal to 1. So the new vector, that is C vector, is, what is the C vector? C vector, this is my C vector. It is U vector, it is X vector, and it is my C vector. So here what will happen? From these equations we can observe that directly x3 is equal to 1, substituting the value of x3 in this equation, x2 is equal to 1, substituting the value of x2 in this equation, x1 is equal to 1. So x1, x2, x3 all are 1, 1, 1. This is the required solution of the given system of equation. Now solve as two triangular system without multiplying LU and to find A. So here directly again similar pattern. This is my L, this is my C, this is my B vector. So I'll get my C. Here in this case solving which we got our C is 2, minus 2 and 0. That is, now it is Ux is equal to C. So from here we will get our x3 is equal to 0, x2 is equal to minus 2 and x1 is equal to 5. Substituting in this equation, because first equation is 2x1 plus 4x2 plus 4x3 is equal to 2. Here substituting the values we get x1 is equal to 5. So we got x1, x2, x3. x1 is 5, x2 is minus 2 and x3 is 0. That will give me the solution vector. Okay, next is this equation question. So here what we will do in the first matrix, just one row interchange, first and second row interchange will give me my target achieved. So here if these two rows are changed, that is, what is my P here? 0, 1, 0, 1, 0, 0, 0, 0, 1. If I multiply this matrix with A, then I am getting a matrix whose pivots can be eliminated, whose pivots can be obtained, and it can be LDU factorization can be obtained comfortably. There is no issue. But in this matrix, one can observe that here when I am doing this R2 minus 2R1 stored in R2, I am getting my second row, whole row is becoming 0. R2 minus 2R1. So this minus twice of this minus twice of this minus twice of this. What I am getting? I am getting my 0. Hence, we will get a zero row. That means one of the pivot is missing. But LDO factorization is possible only when all its pivots are existing, or all its pivot it has. When it is non-singular, only then LDO factorization exists. So for the second matrix, LDO factorization is not possible. Now find a 4 by 4 permutation matrix that requires 3 row exchanges to reach the end of the elimination, that is U is equal to identity matrix. Observe here, this is a permutation matrix, and here what are the operations I have to do? I have to go for first, to get identity matrix from this, first these two rows should be interchanged, then these two rows should be interchanged, then these two rows should be interchanged. So this is a matrix on which 3 row interchange operations are to take place. After applying 3 row interchange operations, we get our identity matrix. And this is one of the example. Now question 17, it is not to be discussed now, later on it can be discussed. Now observe here question number 18. In case of question number 18, one can observe that the second equation minus third equation, second left hand side, I am telling about LHS, left hand side of second equation, left hand side of third equation minus second equation gives me first equation. That means left hand side I am telling R3 minus R2 is equal to R2 is equal to R1 for the first matrix I am telling. But the right hand side is something different. So they are the left hand side, this row operation takes place, but right hand side it is not happening. Hence it is a singular system of equation with no solution. And the second case, this is a same coefficient matrix. So it is a singular matrix having infinitely many solutions. And in the third case, if we write it as an augment matrix and apply elementary row operations on it, we will get it has all the 3 non-zero pivots in the echelon form. That means it is non-singular. Hence, it has full set of pivots and it has unique solution. Now let us discuss this. What it is telling? This is my A matrix. What operation I should do to get here 0? First, to get here 0, what operation I should do? It is 1, 1, 1, 0, 2, 3, 0, 4, 0. So here R2 minus 2R1. So what is E21 here in this case? E21 is nothing but 1, 0, 0. It is 2, 1, 0, 0, 0, 1. It is E21. Similarly, what will be E32? So here again, it is R3 minus 2R2 stored in R3. So how much I will get? So here, what is my 3-2 position matrix? 3-2. It is, in place of 3-2 position only, there will be 2 rest all elements. E32 is equal to 1 0 0 0 1 0 0 2 1. This is my E32. And what are their inverses? If its inverse is required, write here -1. If its inverse is required, write here minus. Bus. So substitute there in the given steps, you will get your desired result. The same process can be repeated here. For this also the same method, nothing new here. Only two spaces were there. Here third element also exists. So here also we can go for the same process, but three matrices will be there, which can be comfortably achieved. Similarly, this is a diagonal matrix. So here already it is a triangular matrix. A is a triangular matrix. As it is in upper triangular form, so this is my U. So what is my L? L is identity matrix. And in case of LD, it is for LU factorization. For LU factorization, LD, so what is my U? U is given matrix A. U is given matrix A, and here this L so here LDU factorization is nothing but L is identity matrix and D is 2 3 7 0 0 0 0 0 0. And what is U? It is 1 2 4 0 1 3 0 0 1. This is my L. So why this we will leave? Let us write that also. So what is my L? My L is 1 0 0 0 1 0 0 0 1. Okay, so it is my L, it is my D, it is my U. Okay, so there is no issue. Similarly, the other questions can be attended here. Now this is a question number 29. Here this is my A, and I will do the operations that first R2 minus R1 stored in R2, R3 minus R1 stored in R3, R4 minus R1 stored in R4. It will give me this matrix. Then my first pivot is over. Its task is over. Then for second pivot, R3 minus R2 stored in R3, R4 minus R2 stored in R4. It will give me this matrix. After getting it, again, I have to make this element also 0. So what to do? So to make this element 0, again, what I will do? R4 minus R3 stored in R4. So up to third row, there is no change. So here, the fourth row, this will be 0, and this is D minus B minus C plus B. So B cancels, so it is D minus C. So now this is in echelon form. This is my echelon form or U. So here, this is a pivot, this is a pivot, this is a pivot, and this is a pivot. This matrix is non-singular, or its LDU factorization is possible only when all the pivots are non-zero. That is, A is not equal to 0, B is not equal to A, C is not equal to B, and D is not equal to C. That means all four of A, B, C, D are distinct and A is not equal to 0. Then regarding this. So here Very simple, in the same manner as we have done in the previous question, one can convert these two matrices into the corresponding factorization. So for example, the second matrix, which looks something difficult or complicated, it is not at all complicated. It is just put here in place of B, put 1 in place of C. In this matrix, in place of B and C, you put 1. In place of A also you put 1, you will get this matrix. That means if I do this, it can be done for the first one. So for this matrix, what to do? For the second matrix, for this matrix I am doing R2 minus R1 stored in R2. It is A0, 0 B 0 B plus C. Now what I will do? This is to emerge 0. So what to do? R3 minus R2. This is a pivot element. This is already a pivot element. So R3 minus R2 stored in R3. How much I am getting? A0, 0 B 0 0 C. Now it is in upper triangular form. There is no doubt about it. And to do this, we got, what is our L? L is equal to E21 inverse into E32 inverse. That is 1 0 0 1 0 1. In place of 2 1, it should be 1. In place of 3 2, it should be 1. This is 0. This is my L. Already I got my L. This is my U. And this U can be written as dV. How to write down the dV? Is equal to dV. That is that A, B, C, 0, 0, 0, 0, 0, 0. This is my D. And what is my V? 1, 1, 0, 0, 1, 1, 0, 0, 1. This is my V. So LU factorization means we will write this L and this U. LDV factorization means L, this is my D, this is my V. We can write. So already we have written several times. So finally it can be done. And this question and this 32 and 33, like this several questions we have done several times. So now we will again not repeat the same process. Now let us come to article 1.6. Here the article is inverse, and we know some of the properties of inverse. If A is a diagonal matrix and A inverse exists, then A inverse is equal to all its diagonal elements are reciprocated. That means if my A is equal to A0 0 B, then what is my A inverse? 1 by A 0 0 1 by B. Diagonal matrix. It is one of the property. Again, for any ABCD matrix, A, B, C, D, this is my A, then this implies A inverse is equal to 1 by AD minus BC DA minus B minus C. This is the formula for any matrix. Okay, now let us go to discuss. Let us discuss about the question number 4. A is inversible, it is given, and also given AB is equal to AC. Prove quickly that B is equal to C. Let us multiply A inverse from the left hand side of both the side of the equation. Then what will happen? By associativity of matrix multiplication, it is identity, and from these two identity matrices we got B is equal to C. Next part of the question is, A is given. Find an example of AB and AB equal to AC, but B is not equal to C. So here, as A is having last two row elements 0, 0, whatever I will multiply to the whatever I have the elements in B and C, the last row, whatever it contains, it has no impact. So here, let me write BC, B is equal to this one and C is equal to this one. And what about AB then? Then in that case, what is my AB? AB, it is 5, it is 0, and then this is 7, it is 0. And what is AC? Again 5, 7, 0, 0. This is 0. So what I got? Even if my B and C are different from each other, but AB is equal to AC. So this example is over. Now, use Gauss-Jordan method to find out inverse of this matrix or to invert this. Already these questions are done while explaining this method. So you can go through the previous video. Here we are expected to write some examples of A and B such that A plus B is not invertible, although A and B both are invertible. So take two diagonal matrices where the diagonal elements are non-zero elements. That implies here A and B, they are having full set of pivots, hence they are non-singular, hence they are invertible. But A plus B is having only one pivot, another pivot is missing, so it is not non-singular, so it has no inverse. Second question is, find an example where A plus B is invertible, although A and B both are not invertible. So here what I have done, this is my A which is singular, this is my B which is singular, so their inverse does not exist, but A plus B is having, it is full set of pivots, so it is non-singular, so its inverse exists. Similarly, third example is asked that where all the three are invertible. So here full set of pivots, so inverse exists. It has full set of pivots, inverse exists, and A plus B has full set of pivots, hence inverse exists. Next question is, in the last case, use A inverse A plus B into B inverse is equal to B inverse plus A inverse to show that C is equal to B inverse plus A inverse is invertible. Also find the formula for C inverse. So here what we will do, if we get C inverse, then that means, and we multiply C into C inverse, and we are getting identity, that means C inverse, C is invertible, and we have inverse, the inverse is this much. So observe here, the value of C written here is something 3 terms. Suppose X matrix, Y matrix, Z matrix, I want to find out its inverse. It will be Z inverse, Y inverse, X inverse. So here same thing. So here X is A inverse, Y is A plus B, Z is B, B inverse. So their inverses are, this is Z inverse, this is Y inverse, and this is X inverse. Okay, this is B. This B is nothing but your Z inverse, Y inverse, it is X inverse. So here substituting the value of C, one can observe these two are becoming identity. Once they become identity, they vanish. Then these two again they are inverses of each other. That's why they become identity. Again they vanish. Last is A inverse A. So again they form identity. So finally it is I. So C into C inverse. Similarly, C inverse into C, if we substitute and we multiply, we get identity matrix. So C inverse exists and its value is given here. So this is my C inverse. And how I got this inverse? As I have told, I have applied the properties of matrix inverse of multiplication of matrices. Now A is given, it is invertible. Which of the properties of A remains true for A inverse? A is triangular implies A inverse is triangular. This property will be the property. But still I have some confusion regarding this at present. Better we will discuss further. So it is not yet discussed. Next question is, this is given A vector, this is given B vector. What is A transpose B? A transpose B is 3 into 2 plus 1 into 2, that is 8. It's a scalar. Then what is B transpose? B transpose A. Again the values will be same. That is 8. What is AB transpose? AB transpose means 3, 1, 2, 2. The values will be 2 cross 2 matrix, that is 6. Two, it is 2. Okay. Similarly, what about the other case? BA transpose. BA transpose means B is to 2. This is, and A transpose means 3, 1. So how much it will be? It is 6, 2, and it is 6. They are transpose of each other. Okay. Next is, so that B plus B transpose is equal to A is always symmetric. We know transpose property, we will go for that. A is equal to B plus B transpose. That implies A transpose is equal to B plus B transpose whole transpose. That is equal to B transpose plus B transpose transpose. That is B transpose plus B. But matrix addition is commutative. So that's why I can write it as B plus B transpose, which is equal to my A. So what we got? We started with A transpose and we reached that it is equal to A. So this implies A is symmetric. A is symmetric. Similarly, for K, here for K we have to substitute this. K is equal to B minus B transpose. That implies K transpose is equal to B transpose minus B. That is equal to how much? That is equal to minus of B minus B transpose, that is equal to minus of K. So K transpose is equal to minus of K, hence K is skew symmetric. So here A transpose is equal to A, hence A is symmetric. Here K transpose is equal to minus of K implies K is skew symmetric. So this part is also over. Next part of the question is, B is given. Write B as a sum of two matrices. One is symmetric, another is skew symmetric. 1 3 1 1. Applying the same formula, we should do it. B is equal to 1 3 1 1. B transpose is equal to 1 3 column wise 1 1. Now B is equal to A by 2 plus K by 2. This is equal to how much? B plus B transpose, it is 1, it is 2, it is 2, it is 1, plus B minus B transpose 0, 1, 1, 0. So here we got our desired result. How many entries can be chosen independently in a symmetric matrix of order n? As it is a matrix of order n, above the matrix, we will write here answer. Okay, so here as it is order n, likewise n elements will be there. This is here also row wise n elements will be selected, then here n minus 1, and then here here n minus 2, and finally this is 1. So if we add this 1 plus 2 means 1 plus 2 plus 3 up to n, that means n into n minus 1, n plus 1 by 2 number of ways, 2 number of distinct elements I can write, because rest all elements are same. So here rest all elements are same. So how many choices are there? I have n into n plus 1 by 2 number of distinct choices are there. For K, for a skew symmetric matrix, how many can be chosen independently? Here the diagonal elements, n elements, are not chosen. All of them are 0. So that means 1 plus 2 up to n minus 1 number of elements I can choose independently. That is equal to n minus 1 into n by 2. This number of elements I can select freely. So here, these are the last questions of this series. After this, we will stop this video. We have to discuss whether it is true or false. If it is false, then we have to give counterexample. If it is true, then we have to give the reason. A 4 by 4 matrix with a 0 row or row of zeros is not invertible because one of the pivot is missing. So A has not full set of pivots. So it is not. It is singular. Hence, it is not having inverse. Because a matrix should be non-singular to have its inverse. So here a 0 row is there means one pivot is missing. So it is not having full set of pivots. Hence, it is singular. So its inverse does not exist. So it is true. Next, a matrix 1 matrix with eyes or ones down the main diagonal is invertible. Not necessarily. For example, down the main diagonal, if it is 1, then there is no information regarding main diagonal. So it is 1 0 0 1. Okay. So here ones are, this is a matrix where ones are there in down the main diagonal, but if this element is 0, then it has one pivot missing, hence it is not invertible. So it is false. A is invertible, then A inverse is invertible. Yes. If A is invertible, then A has full set of pivots, and the relation between the pivots of A and A inverse are they are reciprocal of each other. So if A has all non-zero pivots, then A inverse has 1 by A, 1 by means all the pivots of A inverse are also non-zero, which are reciprocal. For example, suppose A has a pivot A, small a, then 1 by A will be pivot of A inverse. So if it is non-singular, then it is also non-singular. A transpose invertible, then A is invertible. Yes, it is also true, because A transpose and A both have same number of non-zero pivots. If A transpose is invertible, means A has full set of pivots. That implies A transpose has full set of pivots. That implies A has full set of pivots. Hence, A is invertible. So this is true. This is also true. Now, for which value of C, whether this matrix is not invertible. This matrix is not invertible. So clearly, for 3 values of C, it is possible. C is equal to 0, C is equal to 2, and C is equal to 7. So here what will happen? Why it is so? When it is C is equal to 0, the second row will be 0. So a matrix having 0 row is singular, hence it is not invertible. When C is equal to 7, C is equal to 2, the first row and second row will be same. Hence it is not singular. It is singular, so it has no inverse. And if C is equal to 7, this column and this column will remain same. Hence the matrix is singular. Hence it has no solution. It has no inverse. That means its inverse does not exist. So with this, I hope we should conclude for today. Next class we will start chapter 2, that is vector space. Thank you for your patient listening.